Hey everybody, this is Larry. This is me going Q3 of the weekly contest 436. Count substrings divisible by last digit. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. I would say, first of all, apparently there are other ways to solve this problem-ish. You still need to call part of what I did, but I solved it in a way that was just, for me anyway, very quick. And honestly, even though I did it in 14 minutes, I actually had a typo that ate up a couple of minutes. So I was actually kind of fast on this one, if you ask me, like by my standards. But yeah, so the first thing to note is that this is very tricky, right? I guess that's the first thing to know. Thanks, Larry. It's a hard problem. Thanks for stating the obvious. But no, but the key thing is that yeah. So well, first of all, it's a contribution problem, right? How I want to think about it initially, anyway, as a contribution problem, right? Is that for n is 10 to the fifth, and as a result, you can't really do n squared, right? For the substrings, this is a substring problem. So then you ask yourself, okay, well, for each digit, what is its contribution to the answer? And yeah, so for example, let's just say we're going from left to right, and then in this case, you can build on stuff, but I guess you don't really have to. So yeah, I don't know. But yeah, so you go from left to right, and then for each number you go, okay, well, what is the contribution to the answer? Well, if this is 0, we just kind of ignore it, obviously. But yeah, it turns out there are a couple of ways to do this. For example, if I is equal to 1, or like if the digit is equal to 1, then every number is possible, right? So that means that in this case, this 1 has 4 possibilities, because 1, 0, 1, 7, 0, 1, and 5, 7, 0, 1, right? And then the same thing is for 2, right? Because everything that ends with a 2 is whatchamacallit, right? Everything that ends with a 2 is divisible by 2. That's just the definition of even numbers. And then you could similarly do it for what people call divisibility rules, right? Divisibility, maybe I misspelled it, right? Oops. And for 4, what is 4? Actually, I don't know the divisibility. I'm not gonna lie, I do not know the divisibility rules. But yeah, but for 4, so I'm looking it up now, honestly. I didn't do it this way, just to be clear, clearly, right? So 1, every prefix. 2, also every prefix. 4, apparently, last 2 digits are divisible by 4, then every prefix, right? So yeah, 8, is it just like 20? Last 3 digit maybe? 8 is last 3 digits are divisible by 8. Every prefix before that then, right? How do you do 2? Oh, I guess it could just be zeros. Yeah. Okay, well. Yeah. And then there are also things like 3, which is, sum of the digits. And here this one maybe is a little bit, I don't know how people did it, but if I had to do it this way, then it is just yeah, it is like a very straightforward DP, right? In that it is the digit is a DP on the sum of the digits, and then you just count the number of things that are 0, right? Sum of the digits are divisible by 3. So I didn't do it this way, so maybe this part is a little bit hand wavy, but this DP for some of the digits are divisible by 3 should be easier than what we're doing later anyway. So yeah, and then DP, right? And then what's it? 5? Oh, 5. Well, also keeping in mind that the last digit is 4, so that limits some stuff, right? And last digit is 8. And the last digit is 3, which is last digit. And last digit is 5, so it's actually every prefix as well, right? Because it always is going to be. 6 is going to be even, and the 3 rule. Am I missing anything? 9? Oh yeah, 9 is sum of the digits are divisible by 9. also DP maybe. Again, I'm not gonna go over these, but then 7 is the tough part that people tell me about, right? I don't know. There's some like crazy things here, but yeah, DP. But in any case, so yeah, and then once you do that, it will be a lot faster, right? But what I did is just dynamic programming for the contribution. How do I think about this? So I think about it one digit at a time. I mean, I'm going to use 7 as an example just because, well, you need it for both ways anyway. And I'm not going to go over how to implement all the other ones just because, well, I mean, why do I need to, right? But yeah, let's just add like a couple of 7s for science, right? So then here's 7. What am I trying to do at this point, right? Let's say I'm doing a DP. Well, at this point, I want to know how many prefixes are divisible by 7, right? So then, of course, you have all these things, which, oops, you have this number as a prefix, you have this, you have this, oops, and this, right? So that's the way that I kind of want to think about it. And here is the key part is that, and there are a lot of permutations you can mess around with, honestly. But the way that I think about it is that, okay, starting with 5, right? So this number, what is this, right? It is, what is it called? What is that? Horner's rule? Horner's method? Yeah. I mean, Horner's rule is something else, but or Horner's method is something else, but you can think about this as 5 times 10 plus 7 times 10 plus, oh, this is in parentheses, of course, plus, well, in this case, whatever, but, you know, and so forth, right? Did I do that right? I think I messed up. Sorry. It's actually 5 plus. No. I think I did it the other way. It's 5 on the inside, right? Clearly, I need a refresher. And then 5 on the inside, and then it's going to be 7 plus this thing times 10. 0 plus this thing times 10 and so forth, right? And the key thing to note is that under this Horner's method is that if you mod it every step, it is what people want to let's say is it's closed under what's it called, modular. I forget what it's called, modular arithmetic maybe. I don't know. Under modular. I'm really bad at the terminology today, so my apologies, right? But what that means is that, at least for the addition and multiplication, right? But what that also means is that you can kind of just do it every step of the way, right? Because of the other identity of that, 5 mod 7, or rather 5 times is equal to 5 mod 7 times 10 mod 7, right? Something like that. So that's also a thing, right? So based on that, then now you just kind of figuring out, okay, so now I have all these kind of ideas in my mind, and maybe I'm going a little bit wonky and a little bit, okay, then here we go, well, what if we start here? What would that look like, right? So let's say we have this one. So then you just kind of do the visually think about the math. You go, okay, first it goes 5, and then now it goes to 57. So because 5 times 10 minus 7, 5 times 10 plus 7 mod 7, right? So what is that? I don't know, 749, 749, right? 56, right? So that's 1, right? And then now 1 goes to 10 because of the next digit is 0. So then now it goes to 3. And then now the 3 it's now plus the next digit of a 1. So then you have 31, so 28, right? So it also goes to 3. And then now you have 2, so 32, so it's a 4. And then now 4, 7, what is that? 5, right? Maybe I'm going really fast, so I don't know if this is so I don't know if this is going too fast. But that also means that by the time we go to this 7, this means that this is no good, right? Because why is it no good? Well, it's no good because this is not 0, so if it's not divisible by 7. That means that this number is not divisible by 7. Okay, we'll try again. So for 7, we go, so 7 mod 7 is going to be 0, so we're pretty good. But then now we add a 0, so still pretty good. We're still at 0. We add a 1, so it becomes 1. It becomes 12, which is a 5. And then 57, which is, I don't know what that is, right? What did I say it was? 49, 56. Man, I suck at math. So this is 1, which is also no good, right? So here we start at 0. So then we have 0. I mean, I'm being lazy, but you also technically being lazy is good because you can see that we reuse this, right? So at here there's 0, so we reuse it. So you can see that we do the math in an extra kind of way. And then here's same thing, right? So wow, actually, maybe I should have chose one where there's some kind of good, right? So 2 to, what is it, 21, so 6. Right? Like I said, maybe some of this is wrong, right? But yeah. But that's basically the idea. And of course, if you simulate this all out, this is going to be too slow, right? Because, well, if you look at the last digit, if you have the last digit, then this is going to be n squared because we have n strings or n prefixes, and each of them is take about n time. Not quite each of them take n time, but whatever, right? It's going to be n squared anyway, which is too slow. But what happens, right? What happens is that every step here, if you kind of look at it vertically, right? Then now you can collapse them a little bit. What do I mean by that? What I mean by that is that, okay, if you look at it vertically, there's a 5 here. So then you can maybe just say there's only 1 5. And then here, well, now there's 1 0 and 1, 1 0 and 1 1. So maybe you could just store that instead. It's more obvious when you get to here, right? Because then now you go, okay, well, also this looks a little bit wrong because this should be an offset. So I probably did the math wrong somewhere. 10, 3, 30, 28. This is a 2, right? So I did the math wrong. 22 is 1, and then wait, am I doing it wrong again? 30, 28 is 2, and 1 is 1. Oh no, it's 31, not 30. So this is 3. Maybe that is right. I don't know. 30 and then 32. So that's gonna be what, 24, and then 47. It's, let's say 5. Okay, I don't know what I had, but maybe this is right. I don't know. That's not the key point anyway, because the computers can do this for us. But the key is that we have 3 and zeros. Well, the thing is that the zeros are the same, right? So we don't have to. We know that every step of the way in the future is going to be deterministic. Whatever we do, it's going to stay the same. So that's basically the idea, is that we're just going to collapse these zeros together. And here, now all the zeros, we just have 2 zeros, and then we, of course, we have to add in a new digit of 1. But otherwise, this is also the same, right? We have 1 3, 3 1s. And then next, we have 1 4, 3 5s, because the ones, every single one has the same answer of doing a 5. And then next number is 2, because that's the next number. And that's really the idea, is that, okay, well, how many numbers are there per column, if you will? Well, there's only 7, right? 0, 1, 2, 3, 4, 5, 6. So that's basically the key idea behind this one, is that for each digit, we can just keep track of 6 numbers for divisible by 7, and then just keep track every step of the way. And yeah, and actually it turns out you can replace this with any number, and of course you only check for this 0 if the last digit is 7, because that's just what the problem actually calls for the last digit, right? And that's it. that's basically the idea. And you can actually use. There's nothing special about the 7. I just use 7 because I don't know. It makes sense. But you can actually even do this with 2 or 4 or whatever. I mean, of course, you have to kind of change certain things a little bit, but you can use it for every number. Everything still holds everything we talked about. So that's basically the idea for this one, right? So basically here I go to add a note is what is the contribution of. So there are a couple of ways you can do these loops actually, but I just wanted to do it because in theory you can do them all together, but it would just be more space. For example, you could put this I loop inside here, so where I is the previous digit, or I is still the digit that we're processing. J is the previous digit, right? So here I is the I is the contribution, or is the number we're solving for, right? So this could be like, so with I is equal to 1, then this should add up all the numbers where 1 is the contribution, right? And so forth. And here we just set, I number of different numbers because that's just how it goes. And for X is in S, this is for every digit. We convert it to int. Maybe I could have taken this out actually, but anyway, yeah. And then we just set a new R, right, for the next row, and then here we shift by 10 and add as we said, right? So for each previous digit that we care about, and this is a count, right? So this is a number with a count, and for every one of those we add it to the previous one. And this is where actually I spent a couple minutes. Is for some reason I wrote this instead of add, which was just not right. I mean, that's the TLDR. I thought that because I think initially I thought that they all kind of mapped like in a diagonal kind of way, but I think I'm actually wrong on this one due to because you're shipping by 10 and not I. So as a result, you actually kind of you need to do this plus minus thing. But yeah, I think for 7 it actually doesn't matter, but maybe I'm wrong on that one too. I don't know. Either way, this one is right though. So yeah, and that's how you solve it. Is that for the new row? Or this is the previous row is J, and then the new row we shifted by 10 plus X, and then we set it. And of course, we want to add the current number that we're processing at the base digit level, and we increment. And then yeah, and then if X is equal to I, which is part of the last digit that this problem asked for, then we just add it to the answer, and that's it. Yeah, that's it. And this is just shifting to the next row. It's almost like the space optimization, but it's just easier to write that way. So what's the complexity here, right? It's pretty straightforward to look at. This is n, this is 10, this is also 10. So it's about 100 times n, which is a little bit tight, which is why in the real time, this actually passed, but during the live portion, I actually converted to Java. Because I was a little bit worried. That's why if you look at this, it took the word Java. But yeah, that's basically it. This actually in Python took about 5 seconds. So this is actually kind of, where is it? Yeah, this took 5 seconds. So I guess it would have been fast enough, but it's just very sketchy. If you watch the live portion, I actually test for a big N, and that took like 0.6 seconds each. So if Leetcode was a little bit ungenerous, then but Java was very fast, as you can see, so I didn't worry about it. I just wanted to see. So the thing that I like, if I could do it again and I was much smarter about it, I just didn't want to think about it. I could maybe if I is equal to 1, maybe just we don't have to do all the rules. All the rules are kind of annoying, honestly, but we can definitely do 1 and 2, right? So we can do that, right? Maybe. Yeah. Maybe we can allocate this, but just ignoring it. So yeah, so if I is equal to 1 and X is equal to 1, then yeah, and then we just continue, right? So in this case, we just, well, I guess you have to add the number of prefix in this one, right? So maybe just go ahead index, right? So that means that, yeah, so We add it by index plus 1, right? Because if you're at the ith index and index plus 1, we continue. And then already that probably saves you a lot of time, right? Yeah, and actually, if I is you don't even, this is only if x is equal to I, then here we actually even skip this part for I is equal to 1. So this is, yeah. Let's take a look as to see, let's make sure that is right first before I say anything. But yeah, but it should be at least faster, right? So yeah. Oh, huh. Maybe I'm apparently not that much. Maybe I is equal to 1 doesn't come up that much. Huh. That's actually surprising that it doesn't save that much time. But you could even just write like, you know, if I is equal to 2, then if x is equal to I, you do the same thing, right? Yeah. 2 and 5 maybe. So maybe if I is in 1, 2, 5, right? Let's see if that saves us some time. But already we're doing a lot less work. In theory, you probably can maybe take it out the loop. Maybe there's some like weirdness there. But yeah, you can see that this actually saves. Actually, honestly, I did expect it a little bit more savings, but in any case, so yeah, so you kind of see how much time you save with these things, which may or may not be helpful. I don't know. Yeah. Anyway, that is all I have for this one. Let me know what you think. Yeah, I think the DP part though, it does come in handy in a lot of times and places. So definitely be familiar with the idea of just like counting and kind of grouping them together. I don't know that I've done exact things before. I don't know, probably have honestly, but I think the idea is what stuck with me and able to reconstruct it as a result. But yeah. That's all I have for this one. Let me know what you think. Thanks for watching. And you could watch me solve it live in the contest next. Because it depends on their input. It's a little bit... I mean, I know it's m log m, but... Wow, 2 hearts. Did anyone get this one? No? Okay. Still, what a weird problem. Alright, let's go. Okay. I don't know how to do this one. But is it substring or sub the n square? How do I want to do it? Contribution, of course, but there's only 10 digits, right? So that's fine. Yeah, okay, that's not bad. I got it. Probably, hopefully. So shift and add, shift and add. Well, I guess it starts at 1. Shift and add x or sub I, shift and add. No, you need the mod, I know. Okay, fine. Right, so if x is not equal to 0, no, this isn't right. It's kind of right, but it's not right. What am I doing? I'm missing a piece. Okay. What I want is, let's say right? Is this but I'm missing one thing. I had it in my head, but I forgot. No, you have to keep track of the count, not just the mod. Is this times another 10? But is that right? No. We could do it for every 10 digit, right? So that's not that big of a deal. Yeah, okay. No, but that's 10, that's 100 times 10, that's too slow. 10 million? Is it too slow? Maybe it's only too slow in Python. Okay, focus on getting it right first, and then we'll convert it to Java if necessary. That feels right though. 10 million feels right. Okay, fine. Yeah, okay, that feels right. Okay, yeah, fine. Okay, and then now we want to say, okay, and every previous number no, the I doesn't exist. Every previous number we shift the new R I see. New R is equal to and then new R sub j is equal to how many we had previously. So this is j times I plus x mod I. So this is the number of new R, and then new R of x increment by 1. And then now, if x is equal to I, then count to x, no, R of 0. And also x is x mod I, which is actually important for some stuff. I don't know. For one, I think it's the key part. And then after that, R is equal to NR. I think this is actually NR, but fine. Someone like this. I think it may be too slow for because Leetcode is silly. Okay, it's not right. It's right for the last one, so that's good. I was only thinking of ones and zeros, so maybe there's something weird about it. Okay, so here. So for 1, it only has one number to end, so 1 has 1. So we have 6, we want 11. So it's undercounting. 2 is 1 and 2, so that's also only one number, 2 number, 1, 2, and 2 and 1. 12 and 2, okay. 3. 3 is 1, 2, 2. 11, 15, 4 times 3 is, or 5 times 4 is 5 times 6. 5, 4, 3, 2, 1, 5 times 6, okay, fine. But, okay, so 3 only has 2, okay, so it's 3, it only has 1. It definitely has at least 2, so that's wrong. Let's start at 0. Okay, so I feel like I think this is right-ish, but I'm clearly wrong here. So 3, 1, okay. 12, shift and add. So this is a 1 times. Oh no, this isn't. It's not times I. It's times 10. Okay. 10, 12, 25. Am I right? Nope. But closer. Maybe. Okay. Okay, this is just wrong because no, this is right. Whoops. Is 2 is gonna be 3, so that's right. So 3 we want 1, 1, 2, 9. Four. No, that's so that should be 3, which is right. Right, because it's 1 represents 223. Yeah, no, that's right. And then 6. No, this is 9. Represents 9. 9 should not have. Oh, am I dumb? Oh no. This is represents 3. So 3 has 3 is right. But then 9 only has 1, which is probably right. No, it should be none. So that's not right. 9. Oh no, it should have 1 because of itself. 29 is not, so okay, so that's 10, okay. 9 has 1. 6 has 4. So 6 has 4, but that's 3 because, well, I mean, I don't know. 1, 2. So this is the 1. Well, this is undercounting because it should always have. Yeah, these numbers are just wrong. It should always have more number, not. Oh, whoops. What a silly mistake. Okay, 11, 18, 25, that's right. What a silly mistake. Okay. Oh man, I don't know how DP anymore. Okay, but then now what we want is if S is equal to some long number. Is that fast enough? 1.8 seconds. I'm not confident about it, so I'm going to convert it to Java. Because this is very silly to write in Java anyway. Oops. Well, not silly as in like in a good way. I'm not confident about it in Python. have to ask it to pre-calculate the numeric conversion because it looked kind of wonky. I don't know how to copy this. Also it converted to ints. So I have to convert it to using long. Okay. Paying the paying the Python text right now. Yeah, I don't know. It's still kind of slow, honestly. I don't know how much of it is just this thing. Okay, let's YOLO. If it times out, it times out. Is this long? Int should be. No, I mean, I think technically it fits. Oh, no, this is fine. Actually, this is for this, not that. Alright, am I confident? Not really, but let's go, YOLO. Okay. Not bad. How many people got it? 63. And 1 people got Q4. I got that one much faster, but Python things, I don't know. Let's see what I mean, let's see what I've gotten it in Python. Maybe I should wait till the end, but I just want to also YOLO submit it a little bit. Yeah, Python seems like maybe it would have timed out, or at least be cutting it really close. Okay, so I don't know. So really not confident. It's not worth the gamble, I think. Anyway, okay, so thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, this contest, everything in between. Stay good, stay healthy to your mental health. I'll see y'all later and take care. Bye-bye.